Hello, Honors Math 3. Let's finish off this section 14.3. We're talking about continuity of a function. All right, let's consider this function f of x. If you're able to print these notes, it would be a little helpful to have something to take away with you. Let's look at this function f of x and just figure out where this function, first of all, is continuous. And then we're going to use these discontinuities that we see and our knowledge of limits to sketch a nice graph of this rational function. So let's take that function f of x, which is x over x cubed minus 4x. Notice this factors, and we want to see where that denominator is undefined. X over, I'm going to factor out an x, be left with x squared minus 4. Factor again. Oops, notice as soon as I have that common factor, I'm going to have a whole at x equals 0, that common factor. And I'm left with 1 over, factor that difference of squares, x plus 2, x minus 2. And this will give me my vertical asymptotes. You can tell right away where this function is going to be continuous. This function, f, is continuous for all x, except where that denominator is undefined. So this function is continuous everywhere except at x equals 0 and x equals plus or minus 2. Alrighty, so we can answer that question right away. But now we're going to use some knowledge that we have to sketch a nice graph of this thing. Let's continue finding the whole. Specifically, we're going to have a whole at 0 something. I can plug in 0 into what's left, and f of 0 will be 1 over, what is that, 2 times negative 2. And I'm going to have a whole at 0, negative 1/4. Okay, so let's start plotting some of these things that we find. At 0, negative 1/4, I'm going to have a hole in this graph. There's a point of discontinuity. I'm going to have vertical asymptotes at that denominator, where that denominator is undefined. So at x equals plus or minus 2, and let's plot those. Okay, remember our horizontal asymptote for a rational function. Since the degree of the denominator is larger than the degree of the numerator, I'm going to have a horizontal asymptote of y equals 0. So let's dash that. Okay, so that's what we know about our asymptotes. Now I'm going to start using some of our knowledge of limits. And I'm going to ask you to think about this. What is the limit as x approaches infinity of this function? And we can use that simplified function. Once we get rid of that hole in the graph, we can use that simplified function to figure out what are the function values approaching as x approaches infinity. Do you remember that horizontal asymptotes are really the same as end behavior? So try to evaluate the limit as x approaches infinity and the limit as x approaches negative infinity of that function. I'll pause for a moment while you think about that. Okay, let's think about this function value. As x approaches positive infinity, this first, I'm going to have a 1 over, that's like 10 million and 2, which is positive, times 10 million minus 2, which is also positive, and 1 divided by this enormously large denominator approaches 0, but it will be positive. So end behavior looks something like this. When x approaches negative infinity, this fraction will be 1 over, what is that, negative 10 million? That's negative. Negative 10 million minus 2, which is also negative. And then 1 divided by this enormous number approaches 0, but it will be positive. So notice that end behavior verifies that that's the same as the horizontal asymptote. So that's cool. Okay, let's look at some more limits. Let's see what happens around these asymptotes. If I zoom into negative 2 from the left, or if I zoom into negative 2 from the right. What is the limit as x approaches negative 2 from the left of this function? Or what is the limit as x approaches negative 2 from the right of this function? Okay, let's think about function values if we could. Okay. As x values approach negative 2 from the left, Let's say negative 2.01, getting really close to negative 2, but from the left. This fraction becomes 1 over, if I plug in negative 2.01, that first quantity will be negative, but extremely small. Negative 2.01 combined with negative 2 will also be negative. So now, denominator is positive. When I divide 1 by something extremely small, the reciprocal of that is something extremely large and growing to infinity. Let's go the other way. Let's approach x equals negative 2 from the right. 1 over, if I plug in negative 1.999999999 to that first quantity, this thing will be positive, but extremely small. If I plug in negative 1.9999999, that is still negative. This will be 1 divided by a negative, very, 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 very small number, which makes the whole fraction grow and grow and grow and grow, which will approach negative infinity. So zooming in from the left of negative 2, I'm growing to positive infinity, but zooming in from the right of negative 2, I'm going to negative infinity. So I have to hit that y-intercept and then hug that asymptote to the left. Alrighty, let's do that from the other side. Or I should say, let's look at that limit around the limits from the left and right of that other asymptote. So let's find the limit as we approach positive 2 from the left of that function. And let's find the limit as x approaches positive 2 from the right of that function. Okay, let's find numbers just to the left or just to the right of 2. So let's say x is equal to, what would that be? From the left, 1.99999. From the right, let's say 2.0001. Plug those into the function and see what happens. Okay, plug in 1.9999999 to that first quantity in the denominator. That's just a positive number. Plug in 1.9999999 to that second quantity will be negative and extremely small. So 1 divided by a negative is negative. 1 divided by 0, very, 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 very small numbers, actually grows to infinity. But this will be negative infinity because of the sign analysis, we call that. Okay, so I'm zooming from the left to negative infinity. Let's plug in 2.0001 will be 1 over 2 plus 2 is 4, so that's approximately 4, that's positive. 2.000, whatever it is, minus 2 is going to be positive, but extremely small. 1 divided by extremely small numbers grow, and that will be positive infinity. And using some limits and discontinuity, I can get a really nice sketch of that graph. Alrighty, we call this sign analysis in calculus. Thanks for kind of trying to figure those out. It's good thinking for us. Alrighty, remember we have a test for continuity. We're going to determine if this function is continuous at some constant, let's say c is equal to 2. Let's remember what it means for a function to be continuous at a point. Alrighty, in a nutshell, the test for continuity is if the function value is equal to the limit. So if f of 2 is equal to the limit as x approaches 2 for that function, then yes, this function is continuous. So let's check f of 2 first. Okay, so we're going to check f of 2. It has to be defined at c equals 2. And what is that value? So yes, this function is defined at c equals 2. If x equals 2, the function value is 2. Okay. To see if that function value is equal to the limit, remember we checked the limit from the left and the limit from the right. What's the limit as x approaches 2 from the left of this function? Okay, from the left, that would be x value is less than 2. Notice I can't plug in 2 into that function because my denominator is undefined. So I'm going to factor that thing. That's the same as the limit as x approaches 2 from the left of x times x minus 2 all over x minus 2. Get rid of that problem spot. Now I can plug in 2. Okay, limit from the left is equal to 2. And my third component here, I'm going to check the limit as x approaches 2 from the right to see what that value of that limit is for that function f of x. And from the right, I'm plugging in 2 into this function. I am defined at x equals 2, so I can simply plug it in. What is that? 2 minus 4 in the top over 2 minus 1. That would be negative 2 over 1, which is negative 2. Okay, and this is a problem right here. Notice the limit as x approaches 2 in general does not exist. Let me wrap this up. So f is not continuous at c equals 2 since the limit from the left of 2 is not equal to the limit from the right of 2. Okay, let's consider some limits of trig functions. If you could pause for a second and evaluate these three limits, that should be no problem. Okay, in each case, as x approaches 0, my functions are nice and continuous at that spot, so I can find that limit. Sine values are approaching 0. Cosine function values are approaching 1. And tangent function values are approaching 0. So those are no problem. These are some other important limits. I think I mentioned these in the review last week on Thursday, and maybe I got ahead of myself. I wanted to give you some time to look at those graphs. Please notice that all of these are undefined at x equals 0. Well, maybe we can fix that problem. Pick up your graphing calculators, play around with the table, play around with the graphs, and see if you can figure out what those function values are approaching around x equals 0. Okay, we've seen this first case. If you plug this function into y1, you might want to overdo it with the parentheses, but I get a graph that looks like this, and my function values as x approaches 0 are approaching 1. Do the same thing with this next case. Again, you might want to overdo it with parentheses as you look at that graph. This is a cool one. Around as x values approach 0, these function values are approaching positive and negative infinity from the left and the right. This function does not exist. Okay? Sometimes in calculus, though, we'll use this function. Find the limit as x approaches 0 of cosine of x minus 1 over x. Check out that graph and see if you can tell what the function values are approaching. Again, with the parentheses if it helps you, and graph that function. My graph looks like this, and my outputs, my function values, are approaching 0. Last case, check out this tangent of x over x and see what those function values are approaching. Okay, this was a cool graph. As x values approach 0, my function values are approaching 1. And as I said last week, again, maybe I got a little ahead of myself on our video. I wanted to spend a little time looking at these graphs. And sometimes these we use so often in calculus that we just memorize them. So we're going to practice those over the next couple days also. All right, so we're going to use some of those properties, some of those limits that we just saw, to evaluate some more complicated trig limits. All right, so how could we use one of those above to evaluate the limit as x approaches 0 of the sine of 2x over x? What would that be? Watch this. For that numerator, I'm going to use a cool substitution. This was a trig identity. Sine of 2x is equal to 2 sine x cosine x. Now I'm going to separate this into a cool product of some limits. I'm going to separate this into 1, 2, 3, a product of 3 limits. The limit as x approaches 0 of a constant function is just that constant. This is that cool little limit we'll memorize, which is 1. And the limit as x approaches 0 of cosine is just 1. Multiply those 3 limit values and I get 2. Okay, and use another cool substitution for this next one. Here's a cool case where as long as these are the same, I'll just let some new theta equal 4x. Now as x approaches 0, theta approaches 0, and I can rewrite this limit in terms of theta. That's sine theta over theta, and using that limit from up above is simply 1. Look at the next one. I have a problem spot in the denominator, factor, and let's see if we can separate this. After I factor out an x, notice this from up above I like. This I'm just left with 1 over x minus 5. This value is 1. Plug in 0 is now okay, 1 over negative 5. and I get negative 1